Greetings everyone, and welcome to a short video on general projectile motion. Over the last few days, including the practicum that we did yesterday, we've been looking at a special case of projectile motion where the object is shot or thrown at horizontal only. Okay, so it rolls off of a horizontal table, or in the practicum it was shot at 0 degrees. And so that just gives us half a parabola of the motion. Today what we want to look at just quickly here is general projectile motion and the extra little bits of math we're going to have to do to analyze it. So here we have a ball which is going to be shot at an initial velocity of v sub o at an angle theta. So instead of being shot horizontally, as we saw with the basketball example earlier this year, it will have a full parabola, the path that it will move. As we did earlier, we can break up that complete parabolic motion into two parts. The horizontal part, which is constant velocity. And remember, that's what's special about the horizontal motion of projectile motion. There's no forces acting horizontally, and therefore no acceleration horizontally, so constant velocity. And therefore we have only one equation, which is really just distance is velocity times time, but to make sure we know it's horizontal, we use x's. This, of course, is what's more commonly known as the range, and sometimes this is even called the range equation. Vertically, since the only force acting here is gravity, hence projectile motion, we know that it's uniformly accelerated, and therefore the four kinematic equations apply. Same kinematic equations we've been using all along. The only difference here, though, is that we need to know what the initial vertical velocity is and what the horizontal velocity is. And if you notice here, it's a little bit of both. This initial velocity here is both horizontal and vertical. How much horizontal and how much vertical? Well, if this sounds like resolving something into its perpendicular components, that's exactly what it is. We can draw the horizontal component of the velocity and then the vertical initial component of the velocity. Now, you'll notice here that I used Vx. I could use Vox, but since the horizontal velocity is constant, it really doesn't matter. The Vx doesn't change the entire time. However, I do have to be specific here to use Voy. That's these Voy's here in the equations, kinematic equations. Obviously, this is a right triangle, and so we can employ right triangle trig. We can relate Vx to Vo and the angle. Right? Vx is the hypotenuse, the initial velocity, times the cosine of theta. And Voy is simply Vo times the sine of theta. Now you could either calculate those numbers, given Vo and the angle, or you could put it in symbols if you wanted to work symbolically. But really it's going to be the same set of equations: horizontal constant velocity, vertically uniformly accelerated motion, the kinematic equations. It's just that we now have a little more complex trig that we have to do on the initial velocities in both directions. You'll see on the next worksheet that I'm going to ask you to find these quantities early on to help you then plug them in later when it comes time to use the equations. So one other little quick thing I want to look at here in this two-dimensional full-on projectile motion. Let's look at this projectile at its highest point. Well, what do we know about the motion of that projectile at its highest point? Well, as we just talked about, the horizontal velocity is constant, and it's Vo times the cosine of theta. So the velocity here initially is Vo cosine theta. The velocity here at the highest point is Vo cosine theta. The velocity anywhere is Vo cosine theta because it's constant. On the other hand, the vertical velocity is a little trickier. Notice that vertically it's going upward till it gets to the highest point, and then it's going downward afterwards. So in other words, it's changing velocity at the highest point, and therefore its instantaneous vertical velocity is 0. Now it doesn't stay 0, otherwise it wouldn't come back down and it gets stuck, right? But it's 0 instantaneously. What then is the vertical acceleration? Well, let's draw a quick force diagram. If this is projectile motion, then the only forces acting are gravity. Is gravity, I guess. And since gravity is acting downward, it gives rise, as we've seen theoretically and experimentally, to an acceleration we're calling little g, and is negative 9.8 meters per second squared. So it's still accelerating at this highest point. Because think about what would be happening if it wasn't. If it wasn't moving and it wasn't accelerating, it would get stuck there. So the object would go up the parabola and then stay at that height and just move to the right, which is silly. That's not what happens. Again, it accelerates because gravity is acting on it, and gravity is unbalanced. Thank you, and I hope you enjoyed the presentation.